Forces come in many different flavors, and if you understand the forces, then in principle you can also solve for the motion of your system. We're now going to discuss a particular kind of force. These are the conservative forces, and that will lead us to the concept of potential energy. Now, for a force to be conservative, we have two requirements. And both of these are important, and you really are expected to remember both of them. The second one tends to be the one that people focus on, but they both have to be true for a force to be conservative. So the first condition is that the force depends only on position. So it means that there's no time dependence explicitly in the force, so that when a particle returns to the same position, we always have the same force acting on that particle at that position. It will not change depending on other circumstances or the velocity of the particle or anything else like that. So this is the first condition that's required for a force to be conservative. Second condition is that the work, which we know is given by this integral, is independent of the path between A and B. In other words, if you start out at point A and you end up at point B over here, it doesn't matter which path you're taking. They all should give you the same total work going from A to B. And that's the second condition. Now, condition 1 means that we can use forces such as the force of gravity. If you look at the force of gravity between two masses, here's a mass of mass m, here's a perhaps larger one of mass capital M. There's a force of gravity between the two. The force of gravity is given by this formula, where r hat is chosen as the direction of the force, assuming that we have taken the second force here as the origin at which we're working. So here's the origin at mass m. So that means that r hat is going to be pointing away from this mass m, so we get a minus r hat on this force acting towards the larger mass here, which might be the sun, and this might be the earth. Okay. But the important part is that, for our purposes right now, is that this force depends only on position, so it satisfies condition 1. Other forces, though, are not included. For instance, magnetic forces depend on velocity. They don't satisfy the first condition. Air resistance, as we've just seen, also depends on the velocity, so it does not satisfy this condition. So F equals V cross B, or air resistance, let's say linear air resistance, minus BV. And they do not satisfy condition 1. Condition 2 is a little more subtle. If you look, for instance, at the force of friction, try to calculate the work of friction. We know that the force of friction is always in the opposite direction of the direction you're traveling. So that's just minus some constant force F, and then it's just equal to the integral over the magnitude of dr. So it's just equal to F times L, F friction, times L, where this is the distance traveled, So if you're starting here at A, going to B, the different paths are different lengths, and therefore the work of this friction going from A to B is going to be different depending on which path you take. So friction does not satisfy condition 2. It actually doesn't satisfy condition 1 either, because the force actually depends not just on the position, but on the direction of movement. Not how fast you're moving, but it depends on the direction of movement, so it satisfies neither condition 1 or 2. Now let's look at gravity near the surface of the Earth. We know that in this case, we have the force equals minus mgy, and that's when you have a particle is being attracted downwards by the force of gravity, and we have picked here, of course, y is being up and x to the right. So let's now calculate the work done on a particle under the influence of gravity. Okay, so we're taking the work of gravity going from A to B. That is minus mg times the line integral from point A to point B of y hat scalar dr, because the force is mg y hat, minus mg y hat. Now this makes it relatively simple to calculate this, because we can just see that dr, of course, is dx, dy, dz. So this becomes therefore equal to minus mg times the integral first of y hat scalar the dx component here, which is 0 dx. Then we get 1 times dy, and then we get 0 times dz. And I could make this division here just because the force doesn't actually depend on position. Well, it's a constant everywhere. So that makes this division rather simple. Also, integration over x and z disappears because the force is only along y. So it is already a one-dimensional integral. Essentially, the only parameter that's interesting here is y. What happens in x and z does not affect the work at all. So this makes this very simple to calculate. It just becomes equal to minus mg yb minus y sub a, which is mg y sub a minus y sub b. And if we're going here from a to b, then this is y sub a, and this is y sub b, vertically speaking. The difference between the two we can call the height, h. So then we just find that this work here, the work of gravity, is just equal to mgh. And this should remind you of something. You've seen this before in 2305. Except then we didn't call it work, we called it potential energy. We haven't quite yet we're not quite yet at the point where we can actually define potential energy, but that's going to be the subject of the next video. But before we do that, I want to treat the important special case of motion in one dimension. So we're dealing with conservative forces in one dimension. So say that we are moving along some curve like this, It does not have to be a straight line, but what's important is that the object, the particle, is confined to moving only along this curve. And let's say that what we really want to do here is calculate the motion starting at A, going all the way to C, and then back again to B. Okay, so that's one possible path in one dimension. The thing is, though, that when you have only one dimension to move in, the number of choices of paths is restricted. It's only back and forth along a line. So what we get then is we want to calculate, let's say now, the work to go from A to B to C and then back to B. That's of course equal to the work to go from A to B plus the work to go from B to C and then back again from C to B. Now this is if we have the first condition on conservative forces satisfied, that is that the work depends only on position, then this is actually equal to minus the work from B to C, in which case, of course, these two terms cancel, and we end up with the work just being equal to the work from A to B. So this gives us that the work is path independent. In other words, in one dimension, if work depends only on position, then it is path independent. And you can show that it works the other way around too. If it's path independent, then the work depends only on position. So remember that in higher dimensions, these two conditions both have to be satisfied at the same time. In one dimension, they are equivalent. And that makes life simpler if we are lucky enough to be working in one dimension. So under that circumstance, we only have to take into account the one condition on a force being conservative. But in all other cases, if we're working on two or more dimensions, then both of these conditions need to be satisfied, and you need to test for both of them. But one dimension is a special case.